Ted has a PhD in nuclear engineering from Penn State. He works in thermochemical experiments and modeling for nuclear fuel development and in-reactor development, or in-reactor behavior, as well as developing advanced nuclear waste forms. He now leads the molten salt thermochemical database work that is ongoing and is taking on the role of Deputy Technical Focus Area Lead for Structural Materials and Chemistry for the NEAMS program. So today he'll be presenting on the MSTDB-TC effort.
Okay, we've been working on the thermochemical database for about 3 years now with various levels of support. Right now we have an NEUP on corrosion-related systems and adding them to the database under the NEAMS program. And we expect that we will have activity continuing on the general expansion of the effort. A lot of folks doing a lot of hard work on the database and related measurements. My group here at the University of South Carolina, Jake McMurray and Caitlin Johnson, when they were both at Oak Ridge National Laboratory, and actually Caitlin was my former student, and so actually did some work on that when she was here with us. And Rob Lefebvre, Khan Aja, and Joanna McFarland at Oak Ridge. So I'm going to talk about just mention the complexity of MSR simulations. I think we all have a good handle on that. I describe the base salt systems we are considering, need for the thermodynamic database, nature of that database, the methodologies we use to generate information and develop the database, including original data determinations, describe the database a bit for you, and show you a couple examples of utilizing it. And I just love these old images of the aircraft nuclear propulsion concept and the MSRE. When you have fuel in the salt, you have a loop in which part of the time the salt is in a configuration where fission can occur, and part of the time when it's not, and where you are instead removing heat from the system. And so you have this 30-second or less residence time in both the primary loop and the reactor core. And during fissioning, you're generating fission products. A number of them are elements of significant interest, such as those that can be radiological hazards, cesiumide and strontium, reactive elements, zirconium, tellurium, and lanthanides that can interact with other phases, as well as the structural materials, noble metals, which largely don't form halides and therefore are going to be present as metals or metal alloys within the fuel salt, and then the noble gases. Besides fission, you have creation of corrosion products, notably chromium halides, but also possibly iron and nickel. And you can get exfoliated graphite, and there's some thought about perhaps some graphite or carbon-containing phases can form, or at least species can form. And then there's always the problem of oxygen and water contaminants and how do they influence the salt. The base salt systems that appear in the roadmap document for the molten salt reactor program include a number of fluoride systems, lithium beryllium with actinides and zirconium, sodium and beryllium with actinides, lithium sodium for thorium fluoride with thorium fluoride, and then certainly sodium and beryllium with uranium and thorium for the thorium cycle systems. Fast reactors are going to be largely using chlorides, and so there's essentially sodium chloride-based systems with magnesium, zirconium, or aluminum, and potentially with potassium as well. And then there are systems where the salt is solely a heat transfer medium. And while we still need to understand that salt, the complexity isn't at that same level of issue. Our point is that We need Gibbs energy relations because they allow us to calculate the equilibrium state of the salt. If you have the thermodynamic values for a set of components, then you can put them in a Gibbs energy minimizer, do calculations, find the lowest free energy state, that's the equilibrium state, and therefore understand the state of your material. Question is, of course, is the reactor fuel at equilibrium? Probably, or pretty close to it, because the fuel's at high temperatures. We know things like to react more at higher temperatures, and it's a liquid state, so things are mixing pretty well. On the other end of the equation, one has to ask, what does radiation do? And I think we have, as we heard discussed, efforts are underway to understand the effect of radiation and how that influences perhaps eventually the chemistry. The equilibrium state is governed by the thermodynamic properties of the materials, their Gibbs energies. But if you know that equilibrium state, you know the local composition and speciation, you know what phases will precipitate, that is their melting points, when they'll precipitate, you'll know what phases can form. You can determine the chemical potential or the redox, and that allows you to control corrosion and transport. You can calculate vapor pressures. You can provide thermodynamic information that's needed for other types of modeling and simulations, such as phase field calculations, and you can determine source terms for accident analysis. To do that, of course, you need an accurate, consistent, and sufficiently extensive Gibbs energy database. You have to have those relations for each phase and gas species. For stoichiometric compounds, we get those values for our database directly from accurately reported values or our evaluation of reported data and or measurements, and we determine our own set of thermodynamic functions for those stoichiometric compounds. However, as nature is wont, we have solid and liquid solutions that need to be represented, and those are more complex, and we have to develop models and then, as a result, values for those models to get Gibbs energy relations that are available for a specific temperature, pressure, and composition. And we treat the gas at the moment typically as an ideal solution, which is a good assumption unless we go to high pressures. So where do we get the information for, and the Gibbs, eventually Gibbs energy relations for these solutions? If this work has been done and reported and is consistent with our database, we can use those values directly from the published literature. Where there are reported models, but they're not our models, they use a different formalism, we have to reassess the systems, or if they use inconsistent base values compared to ours. So it may be very good work, a very good model, it's just not consistent with ours, and therefore will not work accurately with our database. And finally, we have to do full assessments. That means completely evaluate a system, either using both reported values for add new measurements as needed, and eventually develop a consistent database set of values. All that is rolled up and provided in what we call now the Molten Salt Thermal Properties Database, Thermochemical or MSTDB-TC. But we heard earlier today about the thermophysical database that similarly will provide that kind of information for MSR, for the MSR program and MSR developers. The sources, as you can imagine, vary from, again, the directly extracted from the publications to those that we derive from original measurements. In our database, we provide values that are directly traceable to the original sources. That's linked within the database. So we have pure substances where we've taken values from either the NIST database or the SGTE, that's Scientific Group Thermodata Europe, which is available in the FACSAGE equilibrium code. We also have data for melt and solid solutions and complex compounds, and that can come from literature. Directly, as I mentioned, we can use literature information to do our own derivations. We can use sometimes ab initio calculations and modeling to provide data for use in the database. and we make our own original measurements for assessments. All of this information is documented. So there is a trace available from every single value, whether it comes from literature based on our reassessments, from ab initio calculations, or original work. And we link either to the original publications or actually tabulated data. So every value will be traceable back to its source. When we have to develop original values, we use what's commonly called the CalFAT, or calculation of phase diagram methodology. It's very simple. You decide what models you want to use for your solid or liquid solutions. You optimize them to experimental data or first principles results. And the quality is based on essentially reproducing your experimental observations. How good is your model? How good are your thermodynamic values in reproducing the observations? For crystalline phases that are solutions, we use sublattice models such as compound energy formalism. And for liquids that are not salts, we can use something like this two sublattice partially ionic liquid model. So these are common models used for solid and liquid solutions. Molten salts, however, are more challenging. They exhibit short-range ordering. We've seen a lot of development of capability with regard to molten salts come out of trying to understand silicate and silicates, where you see a lot of short-range ordering in liquids. And so we have to be able to capture that short-range ordering to appropriately be able to model a melt. For that, we use what's called the Quasichemical Model. It can account for short-range ordering within reason. You know, it's sort of the practical model that falls between atomistics and it's an ideal solution. So yes, it captures short-range ordering to an extent, but it certainly is not an atomistic model. What it is a practical model that allows us to build up very complex systems in a very convenient way. So we have a couple of sublattices. We have cation and anion sublattices, so we can have the metals on first and the halides on the second. It becomes more simple if we have just a single halide, fluorine or chlorine, and certainly the fuel systems that we're talking about are either fluorides or chlorides. Things get really a little hairy if you want to start dealing with iodine, because now you've got a reciprocal salt with two halides, but we've done that. We can do that as well. The excess Gibbs energy subsystems subsystems are needed. These are what we call the end members, and we allow these sort of end members, these simple binaries, to interact to create the modified quasi-chemical model. And we use data on the liquid's behavior to be able to model the systems, basically fitting values to the preset model parameters. Concept is everything is a quadruplet. We have A2F2, B2F2, and ABF2. And so those are our three possibilities in pseudo-binary systems. And so we worry about the second nearest neighbor and first nearest neighbor interactions. And those interactions then govern the short-range order. You know, stronger attractions between quadruplets means that we've got a greater degree of short-range order. To do that, we need to know things like the cation coordination numbers, and we define those for each of the binary subsystems and apply the requirement of charge neutrality. So that's a very, very simple way of describing a somewhat complex model that we can then regress with data to find interaction parameters and represent the system. In performing an assessment, we need to have our model for liquid, as well as those for other phases in the system, and use whatever available information there is to then represent that and then allow that to then be used in a regression to fit the parameters of the model. So you need information like reported thermodynamic and structural measurements and phase equilibrium measurements. Looking at the potassium chloride, uranium trichloride system, for example, We have a heat of mixing that has been observed for KCl and UCl3 melt, and an estimate for Gibbs free energy for a ternary compound. This is a line compound, a stoichiometric compound. There's also some experimental data out there for a second line compound, K2UCl5. So that all has to be included in the modeling of the system, and it goes into the regression analysis because part of the regression analysis is the melting point. Well, if you don't have the phases into which it melts, because they're not going to be, pure end members, then you have to include any intermediate compounds. A complication is the fact that UCl3 really sees two different coordination numbers. The cations see two different coordination numbers, 6 and 7. And that's its function of temperature and composition. And if you get to really high uranium contents, it can be 8 as well. So we have to accommodate the change in coordination numbers with temperature and composition, and we do that by including additional end members. So here's the enthalpy of mixing between KCl and UCl3. The experimental data you see is the points. The line is our model. And you can see here the concentration of the cations that have 6 and 7 coordination within the model. And once we capture that, then we can appropriately model the heat of mixing, which goes into the regression analysis and allows us to accurately represent the salt. And here is the phase diagram for potassium chloride, uranium chloride. We have a number of reported diagrams, some somewhat better than others. You see a lot of data points on there. Most of those are differential scanning calorimetry measurements that are looking at melting points and transition temperatures. And we are able to see both the K2 UCl5 and the K2 and the K3 UCl6. That's 5 and that's 6 here, and appropriately reproduce their melting points and the phase equilibria. We're unsure of some of the points that were reported, so we made measurements ourselves. So these are ours. The red up point is a DSC measurement of transition temperature on heating, and the blue on cooling. And so we can see that our points fall on Suglobova's et al.'s data lines reasonably well. So we seem to be reproducing that phase equilibria somewhat better than, for example, Hames, who we think made created something of an error in his evaluation. I think we really had the K2 UCl5 phase up here, not the liquidus. So melting point rather than the liquidus. So it gives you a very brief feel of how one performs an assessment using all the available information and a model that has a sufficient complexity to handle things such as the short-range order of the melt. The MSTDB-TC is not export control. It should be available cost-free on Code ORNL GitHub. I'm hoping, after much delay, that we can get this established by the end of this month, and that anyone can register on UCAMs or XCAMs with ORNL and be able to download the database. Along with the database, you have all the backup materials as well as with regard to things such as the sources for all the information. Database follows the FACSAGE ASCII2 format, or this is called DAT format. So here you can see the beginning of the uranium, fluorine, lithium data file. And we are looking at pseudo-binary and higher order systems. So we have reference values for all in the literature with the sources, any original measurements, including uncertainties, and then details of the function fitting and uncertainties. All the systems are validated by reproduction of accepted phase equilibria. So we generate the data file, the thermodynamic data file for FACSAGE that from which we can compute phase diagrams. We compute the phase diagrams, and then we compare them with those that are reported in the literature. So we do that ourselves at the University of South Carolina, and then we pass that to a third party, most recently ORNL, Joanna McFarland has been going through the all of the phase equilibria calculated and reported, and making sure that our models and our thermodynamic values are reproducing the phase equilibria. And that's really the acid test. If you can reproduce phase equilibria, then you got the values right, because the phase equilibria is very sensitive to the thermodynamic values. So that's our quality assurance. Content for fluoride systems. These are the elements currently considered. For the pseudo-binary systems, this is our matrix. So here are the pseudo-binary sodium fluoride, beryllium fluoride, et cetera. And similarly here, and wherever we have a green box, it's in the database. Orange, it's published, but we haven't gotten the database yet. We haven't fully considered it. And blue is being assessed. We don't have any actually blue right at the moment. But we got a lot, not in this diagram rather, but we're continuing to assess systems. Probably put the ones in that we're working on. And then there are the pseudo-ternary and higher order systems listed here. Similarly for the chlorides, higher order systems, and our matrix of the pseudo-binary systems. So this information, of course, is all provided in the data on the code ORNL database hub, GitHub. Here are some examples of the kinds of information you can get from equilibrium calculations using our database. Here is a ternary diagram of lithium fluoride, uranium tetrafluoride, and beryllium fluoride. However, this composition contains 10 mole percent UF3 and 1 mole percent PUF3 at every location. So it's not just lithium, uranium, beryllium fluorides. And so the liquidus temperatures are seen here. So these are the liquidus projections, where these phases that are indicated are the first phases that will precipitate from liquid, in this case, a uranium fluoride, plutonium fluoride solid solution. So you can perform those kinds of calculations. These are done with FactSage. If you have Thermochemica, another code, you can do similar calculations. It utilizes the same format. Interesting questions you can ask is how does additives or additions to a salt affect the properties? So we are looking here at a calculation for FLIBE, which we've added UF4 or PUF3. So here's the mole percent of either one. Here's temperature. And so this is the liquidus temperature. So uranium tetrafluoride doesn't seem to have all that much effect on the liquidus temperature. Plutonium fluoride does. So a few percent of plutonium trifluoride will significantly change the liquidus temperature. And if you are here in your reactor, you're going to be precipitating plutonium fluoride. We're looking at corrosion systems. So very quickly, sodium chloride, chromium chloride, we have assessed that system. You can see the various data. The phase diagram is our computed diagram. This is computed from the thermodynamic values within our database. And similarly for the potassium chloride, chromium chloride system. So we can do a really good job of assessing these systems and providing reproducible phase equilibria. As an aside, sometimes you get very good pseudo-binary reproduction, but then when you interpolate up to the ternary, with a pseudo-ternary with another binary chloride or fluoride, it doesn't work as well. And that's sort of the acid test for these systems. If you can interpolate to a higher order system and reproduce the phase equilibrium, you've done a really good job, because there is not a unique solution for the pseudo-binaries. If you're interested in corrosion issues, and I'll go through this very quickly in face of the time. Here you can plot the RT-ln of the fluorine potential, fluorine pressure. So here's essentially the fluorine potential versus the ratio of UF3 to UF4 in your salt. That's in a FLIBE with 10 mole percent uranium. And that's this line here. So that's the fluorine potential for FLIBE with 10% uranium fluoride at these particular ratios. And you can overlay on that the fluorine potential at which, for example, chromium, this should be chromium rather, down here, reacts with fluorine to form chromium fluoride. But you can do a better job than just doing that. You can say, using chromium activity in an alloy, what is the fluorine potential at which the chromium will form fluoride? So here we've looked at the 71 nickel, 16 molybdenum, 7 chrome, 4 iron, Hastelloy N. There's a model for that that's available for that particular alloy. And so we can use the chrome activity in that alloy to determine fluorine potential at which we're going to fluoride the chromium. I didn't want you to get away without learning that we have a molten salt thermal properties working group meeting, a workshop on molten salt thermal properties, both chemical and physical, thermophysical, next month. It's going to be virtual for a half day on the 15th, 16th, and 17th. We'll have some notable speakers, some of which were here today, and talking about various issues we have with molten salts. It's free, but you do have to register. You can register at the SurveyMonkey or just send me an email and I'll get you in for that. To conclude, thermodynamic functions are important to understanding fuel, and we have a database that is ready to be used and continues to be expanded. Here is the motley crew that has been doing the work in generating the database, and we're looking for new postdocs to join us. So we need help to be able to push out all these values into the database.
What sorts of phase equilibria validation data are you using? Are you running experiments to get that data?
We run experiments to get data we need to generate our models. If we can reproduce the phase equilibria with our models, that's validating the data. And so, for example, you saw the phase diagrams, you saw all the data points on there. Our diagram fit them nicely. That's the validation. Then we do a QA check, have a QA check done to make sure that the phase diagrams are properly being reproduced. The best thing to do is, for very complex systems, is to do exactly what you've kind of implying, is that one should do a benchmark. You know, if you want to understand, well, are you well reproducing a complex system, you need to do benchmark calculations. And really can't escape that, given the fact that the data for these systems comes from a variety of locations, not just our measurements. If it's just our measurements, there would be no problem with QA. But it comes from a variety of sources, some quite old, and you can't go back and know what the uncertainties are.